Last but not least, or maybe least, are the nitriles. They're kind of the odd member of this family, right? I guess that's the surprise for a lot of students to see them put in this chapter. I mean, there's no carbonyl, and we've been doing carbonyls. So why are they showing up in this carboxylic acid derivative chapter? Well, it's because if you throw all those reagents at them, they actually undergo a similar reaction with similar mechanisms and similar intermediates. So they actually react in a very similar way, believe it or not, to a carboxylic acid. So the Spartan rendering of a nitrile is shown here. And notice this polar bond. So there's that triple bond. It's linear. So don't draw any ugly bent ones. Make it nice and linear. So this is acetonitrile, which is actually MECN, which we've seen that before. Back in 211, organic 1, it's a very good solvent for SN2. Polar, but aprotic. So it comes back, or CH3CN. But it's called acetonitrile. That's just its nickname. It doesn't, the aceto part doesn't make a whole lot of sense, except for the fact that it's similar to aceto group, the nitrile is. So the acet indicates a methyl's presence, but usually that means it's attached to a carbonyl. But once again, nitriles are not carbonyls, but they're similar. How? Well, that polar bond indicates, or at least suggests, that this cool area, that carbon, is probably electrophilic, just like a carbonyl carbon. So let's draw that out, that Lewis structure. So in general, here's our, make it nice and linear, right? And as you could see in the electrostatic potential map, it's a little cooler over here by the carbon and hot by the nitrogen, just like a carbonyl, which is why a lot of the same reagents work with it. So what's similar, I would say, is both have electrophilic carbons. So we are going to do the same reactions subjected to the same conditions that we were doing with carbonyls. So let's start with hydrolysis. That's kind of an obvious one from its name, means water is going to hydrolyze it. So break off the nitrogen. Now look what happens. You get a carboxylic acid. Where's that carbonyl coming from? We will see the mechanism. So here we go. The nitrile in the presence of acidic water, basic water or acidic water will give us a carboxylate, which could then be neutralized and work up to form the carboxylic acid. So either one of these scenarios, we can, let's write out acidic and basic. Acidic is usually red, acidic, and basic is usually blue, at least on litmus paper, right? Okay. So, you ready for a mechanism? Well, we know we're going to do a hydrolysis. I'm going to draw the product first. So there's acetonitrile again. But then we're going to have the carbonyl carbon, the nitrile carbon turn into a carbonyl carbon with attached to the carboxylic acid. So how does this work? Well, you'll want to draw out that triple bond for a mechanism for sure. And then remember the dipole. That'll help lead you in the right direction. And I'm doing it color-coded because that nice little Spartan picture helps us remember what those mean, what those colors mean. All right, so if I attack with that alcohol, which I need to look at the point of the mechanism, I need to get more oxygens on there and I need to get the nitrogen off. I'm going to attack the electrophilic carbon. Attack, open. Let's see what I'm at now. I'm going to call this the methyl ME, and then I'm going to start, I'm not linear anymore. I made a bond to carbon and released its triple bond and turned it into a double bond. So now it's trigonal planar. So I'm obeying that geometry. I'm going to draw the OH off to the side and the newly opened nitrile nitrogen there. So let's just make sure there's a full octet around nitrogen. It needs another pi bond. Lone pair. All right, what's next? That's a very strong base to leave nitrogen negative like that, so let's do a proton transfer. Why? I can't get rid of nitrogen while it's negative. That's already, like, because if you have it leave, it's going to take more electrons with it. So I need to at least get it neutral, right? So, but I want to keep my oxygen. I want to lose my nitrogen, keep my oxygen. So I'm going to work toward that. So if I do a proton transfer, I'm going to give the H on the carboxylic acid. So if this H, I'm going to give it to that nitrogen, essentially, and have an O minus. So they're basically trading who gets to be protonated. Now this is resonance stabilized, so it's not a bad way to go. Close that and open that. And we have, once again, oops, I accidentally drew the second pi bond. Oh man, I did that a long time ago. Okay, there we go. N, H, there we go. So need to have, notice there's a lone pair there. I need to have one more lone pair. There we go. I like the looks of that second resonance structure because looky there is a carbonyl. Carbonyl intermediate, carbonyl in my product. I'm on the right track. Need to get rid of this and get an OH in its place. So I'm going to run with this second resonance structure and protonate with some water because I don't have acid available. That'd be very wrong. That would be an example of something unreasonable, is to just add some acid willy-nilly and say, here you go, here's some acid, because look at the conditions, we're in base. You'll never add the acid when we're in basic conditions. All right, so look at what I have here. I have an amide. Well, what do you know? Now this is looking familiar. I'm going to write that in caps. We have an amide intermediate. Well, at some point I ask you to draw out a mechanism with the amide. We've done the mechanisms with the amide, so I'm not going to draw the rest, but we know that amides can be hydrolyzed to carboxylic acids. So that's why there's not so much space here, because that's a whole nother thing. So C, amide, hydrolysis mechanism. So make sure, if you're comfortable with that, that's all we're going to do to shortcut it, because the new part is here. I'm not going to draw the old part over and over again when we introduce it. Okay. So that's kind of gives you an idea of why, okay, makes sense that nitriles show up here, because they work not only are their reactivity similar, they work their way to some common intermediates. The same thing will happen, you'll see, with acidic conditions. So I'll show you that one as well. So I'm going to you always, when you do a nitrile mechanism, you always want to, look at, I'm abbreviating that phenyl, but I'm drawing out that nitrile. That's going to save me some time. Now, just like a carbonyl, in acidic conditions, it's going to be activated. And look over the arrow, I have tosic acid mixed with water. That means I basically have H3O+. Let's go ahead and draw our product. Hydrolysis means keep the carbon, lose the nitrogen, turn it into a carboxylic acid. So now we're going to we're not attacking it yet. We're going to bring the acid nearby and decide, what do we do with the acid? Well, if this is a carbonyl-like compound, what has to happen first? Same first step, activate the carbonyl. There we go. You're getting activated, so it's going to be ready for nucleophilic attack. Look at that nitrogen. It's ready to accept some electrons. Okay, who can attack it as a nucleophile that will allow us to turn it into a carboxylic acid? Better be an oxygen nucleophile. Look over your arrow. Never use acid as a nucleophile. Yep, it's going to be water. Attack. Oh, no, 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 no. I don't attack that nitrogen. What am I doing? Attack. Open. that's on the right track. Give myself a little room right here, so that's why I'm at the top of the page, but I'll bring it back down if I need to. So pH, now notice I'm not linear anymore. I have NH. Actually, I'm going to draw that in a different order because the water came in from below. NH, OH, H plus. Okay, remember we want to keep the oxygen, lose the nitrogen. We're in acidic conditions. We keep things positive as possible. Proton transfer time. That means we strain this nitrogen, so it wants to let go of some of those electrons. The carbon will let go, give it to the nitrogen to help it out. Okay, so now think about this for a minute. We're in acid. We did a proton transfer, and now we have, this is ready for attack, right? It's also ready to accept some electrons. So what do? If I attack, I have a tetrahedral intermediate. But if let's show the resonance kind of like we did last time. If I show resonance, I also close and kick open, if you will, that pi bond. So let's see. What do you know? Doing that allowed me to get to, so I'm glad I didn't attack that imine looking, it's like a mitic acid, imine looking intermediate. So I'm gonna call this, you don't have to know this one, but sometimes it's nice to know that intermediates, imidic acid. I'm glad I didn't attack that, simply because if I did, I wouldn't have this amide that I'm about to get. So if I neutralize this, do I have water? Yeah, I have water. Water is my base. Of course I have water. It's hydrolysis. Amide, there we go. Okay, now this is why I wanted you to draw out the hydrolysis of an amide, so that when we got here, we knew that mechanism already. We were comfortable to say, okay, this is repeat acidic hydrolysis mechanism. So we have a familiar friend here. Just have to wrap this arrow around somewhere where it can get there. There we go. All right, C, acidic hydrolysis of amide mechanism. So when you get to the amide, and this is the moral of the story, you're basically on the right track in the mechanism. Okay, let's do some more reactions that we recognize but are still new at the same time. So it turns out that nitrile, you can add H's to that triple bond just like you would other triple bonds until you're fully reduced to an amine. So that's useful, right? How about the mechanism? Let's go ahead and draw that out. We've drawn out LAH mechanism before with aluminum and everything full all the way. So what we're going to do is just show a way to kind of keep it simple to predict it. But remember that don't drop a carbon here. That's really easy to do with nitriles. They have a carbon kind of hidden in that linear bond. And so now that's the nitrile carbon. right? I got two H's here from the LAH, and the NH2 got H's from the water. So I'm going to do kind of like a mini mechanism because we've done LAH reduction before and it can be longer, but we want something that we can kind of predict if we kind of had to do this a little more quickly on the spot. So that's why I'm going to go ahead and put this in quotes. Because remember, it stays attached to the aluminum really, but I want you to think about what that means if you take the H, the electrons with the H, stays attached to the aluminum, but not forever, right? So the consequence of it is it attacks as a nucleophile open. Okay, so we can think of it that way. And then we're at trigonal planar. And we have a minus charge. So we had only one lone pair. And we have our new H. I'm circling it. There's our new H. Okay. Believe it or not, and this is why I wanted to kind of just keep the mechanism as simple as possible. This is the weird part. It's going to happen again, even though we already have a minus charge. And this is the part that's a little more rare, is that it will attack before neutralizing. It's too strong of a base to neutralize, and notice that the water is not available. It's step 2. So attack open, and now we have our two H's, and we have a dianion, N2 minus. Very unusual because that's not stable. Remember, when we increase the magnitude of the charge, that escalates the reactivity and destabilizes it. Okay, so in order to get home, which I'm not going to show every step, we protonate with water 2 times, right? So that's step 2. So it stays an anion. Where does the water? So if we track those protons, the H's were the red ones, excuse me, the green ones, and the H2O gave you the NH2. So you could do a deuterium problem with that, right? Okay. We have another example. Weaker hydride reducing agent. What would happen? Notice that dianion was very unstable. That's only because LAH is so unstable. So back here, I'm actually going to kind of put something to remind us that this is weird. I don't want to do a wow. That's so I might do like a what happened? It's exciting, but it's concerning. We made a 2 minus. That's not very stable, but it's because LAH is so reactive. This can form because LAH is that reactive. It will just keep, it's brutal like that. It'll just beat it till it gets all its H's on there. However, weaker reducing agent, no. It will not let you form that disfavorable 2 minus charge on nitrogen. So in other words, we're only going to add 1 H. And I'll put that, what I said, in parentheses. It's difficult to form the 2 minus charge ion. Not favorable. So what do I mean by weaker reducing agent? Those sterically hindered hydrides, like Dibol H is a favorite. Diisobutyl aluminum hydride, remember that one? So that'll stop at the aldehyde. So how does that work? And I'm simplifying this once again because we've already done the whole reduction mechanism section. So we're not trying to redo that part. We're trying to see how did we get to an aldehyde instead of an amine, for example. So where did that nitrogen go? Why did we keep the nitrogen in the first one? Why did we get an amine in the first one and an aldehyde here? Very confusing if you don't see kind of the important piece of the mechanism. So like I said, I'm going to keep it simple, but get to the important part because this chapter is really mechanism heavy. So we really want to call out the focal points. Attack open. Same thing as before. We're in basic conditions. Diol is a source of hydride. Okay. We have our delta plus here. So we do our attack open. Okay, that's step 1, and that'll help get you to step 2. Okay, so that's our H that's on the aldehyde. We need to figure out, how did that N ever become, this is a minus. How did that N ever become an O? Well, we're going to stop here. This is the end of step 1. Remember, it will not keep attacking. Diol and these will not talk anymore. It will not make the 2 minus. So it could sit in there all at once, and you're just going to end up with this. So that means it's ready to be quenched with the water. Quenching means we're going to neutralize. So quench it. And so step 2, we'll bring in our water. And we'll relieve that poor nitrogen. Still tracking my H's, and I'm actually going to track the water one in blue. Good. So now, what's the name of this functional group? It's not alkene, it's C double bond N. Something we know. Imine, right? Okay, now we're in familiar territory. If you would like, you may attach the mechanism here, but we know how to get an imine to an aldehyde. That's the imine hydrolysis. Because remember, you make an imine by adding an aldehyde and an amine. So in other words, plus NH3. We lost the N. You make the aldehyde back by adding water, right? And if the water's there, you hydrolyze it. Okay, so that was long enough ago. It's not this chapter, well, neither was the aluminum. But if that bothers you, you want to think about it. Let's see, I already answered imine. But I think I'm going to go ahead and so we all know and love the imine, but we usually hydrolyze with a little bit of acid, and we're still borderline basic conditions. You know, when you put that in there to quench, there's no additional acid necessarily added. It could be. You could actually do your old-fashioned imine hydrolysis mechanism. There is a way to show it just with water. It doesn't actually require necessarily, they'll hydrolyze with water as well. The acid helps a lot though. So, but since it's not listed there, I want to show you what that would look like with water. Okay, so imine. What are we going to do with that imine? Well, we have water. We also have OH minus because we just made it. See right there? So that's probably the stronger, well, it is the stronger electrophile to choose. Attack, open. So I'm putting the imine in brackets because we don't isolate it. And then we have our negatively charged nitrogen. So this was the H from water, this was the H from the hydride. And I'm missing something. My water, my OH. There we go. Okay, so keep in mind what the end goal is. We need to get to the end where we make our aldehyde, and that as a result lose our nitrogen. So let's do that. Let's do proton transfer. I'll do it down here to have some more space. H plus transfer, just so we don't get all squished. So what am I doing this for? I need that nitrogen to go away, so I can't have it charged. And if I take it from the oxygen, that just compels it to go down and kick off, right? Now, yes, that's a terrible leaving group. It's going to quickly pick up a proton and become ammonia. So because so many dislike that step so much, a lot of chemists don't like to see that bad leaving group leaving. This is another kind of fancy workaround for that. That's not, this would be fine to do it stepwise and say, okay, now it goes and gets water right away. But you could also say, I hate seeing that so much. I'm going to let, as that bond breaks, it grabs that proton. You know, it's like, I'm not going yet. But if I'm going to have to break, I'm grabbing that first, right? So as it breaks, it's going to grab that before you get a chance to do anything else. So that's fair. That's another fair way to draw it. So I haven't done, I don't think, that maneuver with you yet, so I wanted to show you that as an option. There we go, we have our aldehyde. That's what we want. Plus, our ammonia comes off. Bonus is that ammonia is actually a gas, so when you do make ammonia, it does drive the reaction forward. Okay, it's nice to see the familiar intermediates. That helps a lot. Another familiar friend, organometallic nucleophiles, carbon-carbon bond forming. So obviously important. Look what we get. We get a ketone from a nitrile. Interesting. Very interesting. I think the nitriles look easy in mechanism, but in practice, they're a challenge because logically, you don't necessarily jump to think that the nitrogen is going to be gone. You really have to think through this mechanism to predict that. So ketone, can we show that so that we can predict that? Yes, we can. So let's show that mechanism. All right, once again, I'm going to draw this out, the whole Lewis structure, and I'll put our Grignard reagent. Remember when we draw the mechanism with the Grignard reagent, this bond, attack, open. Now we are going to have that negative charge on nitrogen. New R group. Ethyl's on there now. That's the job we needed to have done. We add that R group. We're ready. Everything, all the rest of this is thanks to this quenching that I should really actually draw out the H's. Thanks to the quenching, kind of complicates it. It's not a simple protonation. Why not? Because what we made continues to react with the water. Who is that guy? Hey, it's our friend imine again. We know about imine. Same mechanism. I'm not writing that one again. Imine hydrolysis. So that's the one we just did again. Hydrolysis. What does that mean? That the imine breaks up into its pieces. It's carbonyl plus the ammonia. So we'll let the gas, ammonia gas, come off. So all the nitriles will let off ammonia because look at what, and not some other amine, because look, it doesn't have space to attach another R group. So as you work on getting these, because the goal is to separate it from here, the only way to do that is to replace these 3 bonds with 3 bonds to H, hence the ammonia, right? Where does the rest of it go? We get the pH, carbonyl, H. Oops, sorry, new group. That was on the old mechanism in my head. New R group. Okay. Okay. Now I think there is another one. Oh yeah, this isn't on here. So I'm gonna do freestyle. Make some space. I think it didn't make it in the reader. I apologize for that. I think I saw this before. What the last two I want to cover is the opposite of what we've been doing. We have been reacting nitriles, but it's useful for synthetic purposes to know how to make them. We want to be able to make them. So I'm going to show you two ways to make them. So title this to make nitriles. First one is old from Organic 1, but we are reintroducing this now, as if you didn't know, just in case. I think you might laugh and realize you do know. You can take a simple alkyl halide and add a nitrile. Ionic bond, right? So not MECN, but something like NaCN or KCN, it's SN2, good old SN2. So we haven't really thought about that in a while, but that is your first carbon-carbon bond forming reaction. We didn't make this big hoop and holler about it because you don't extend the carbon chain that much. You add one carbon, but don't forget that carbon because it is a little sneaky to forget, really easy to miss. Because now we have that carbon still there, and then don't forget if you draw that in, you have that now. So SN2. So there's one way to make them. Let's try another way. Approach number 2. This is going to be the overall. This is new. If you take an amide, turns out they do react with SOCl2. Just not in the way carboxylic acids do. Carboxylic acids make that acid chloride. The chlorine doesn't stick around. You make a nitrile. What? That's what you should say. I'm glad you asked. What? Because this warrants a mechanism. Good old SOCl2. Let's draw out that structure again. Don't let that scare you, even though it's weird looking. Here's our nitrile. Excuse me, our amide. We want a nitrile. That's our goal. Okay, so we need to lose that oxygen. If we think about that mechanism, we need to explain the oxygen loss. So the oxygen, once again, needs to turn into a good leaving group, which is what the SOCl2 is an expert at. It likes to hang out with the oxygen. So we're going to show the resonance structure where we push the arrows down, and then instead of doing this and drawing that separately, I'm going to do that advanced sort of maneuver that I did last time and save us a step. So instead of pushing up and drawing it separately and say, okay, now that those lone pairs are localized on oxygen, we're going to let them attack. We're going to do this and say, okay, instead of ever resting on oxygen, which is where they were going to go, it's just going to go ahead and attack right away. Attack open. I'll stop there with the number of arrows so it doesn't get too overwhelming. But O minus. I mean, this is starting to get to some good stuff with mechanisms because we want to be efficient with drawing them. If we draw every step out slowly, that's what we need to do when we're learning them. But once you feel like you can handle these quicker maneuvers, you will feel like you can hone in on the important changes much faster. Okay, so what was the result? Here's where I'm at. Oxygen, this swung open and made a bond here, so that's that bond. It has a single bond left with all the R group and all the other stuff that's still there. NH2 plus. Okay. Now I'm going to close kick. We recognize this. Close kick. We're going to. SOCl2 is great because it has its own great leaving groups with it, so it can attach to an oxygen and then kick off its own leaving groups and make more bonds to oxygen, right? Until it's ready to leave, and then take the oxygen with it. So it's basically the whole theater, what's going on here. So here we go. S, one chlorine gone, one to go. We want that sulfur dioxide gas. That's favorable, so we're working toward that. we know that's what SOCl2 ultimately wants to. Okay, so, and R and this guy here. All right, so that's okay if you did it in this order. Now we still have to deal with that positively charged nitrogen though. Some people would deal with that first, then do the closed kick. Honestly, either way is fine. So I'm going to draw out the bonds to the nitrogen because we have to deal with that. Notice we kicked off a chlorine, so we have chloride. That could be our base. Not a good one, but it is okay in a pinch. It's an anion. All right, Cl, S. All right, here's where we're at. Neutral intermediate, what can we do with that? Well, any other chlorine that we have available from a previous step, or I suppose you could use amine too. I'm trying to think of other reasonable bases here. If students use something that's electron rich, I think that's reasonable, but most mechanisms go with another chloride that managed to get free. Okay, so let's do that. Why do I need that? I need to ultimately have a triple bond to nitrogen. How do I do that? I take away the H and let those electrons go there. But in doing that, that carbon has to let go of something. It's not going to let go of that R group, but it will let go of, gladly, the O-S, etc. bond to give us the sulfur dioxide. But we only get the sulfur dioxide if that chlorine leaves. It generates more chloride, so it can continue and that sort of thing, right? So that's always really nice to have as an option. But don't forget we have the byproducts, SO2 gas and HCl as well. Okay, so very interesting method. So in other words, take a step back. What did we do this all for? We wanted to know how to make a nitrile. We can make a nitrile from an amide or from an alkyl halide. Now, I highly recommend you make a nitrile roadmap page with the nitriles in the middle. Have these two reactions going to it, the other arrows coming out with everything from earlier in this lecture, and you will be a happier camper after that. And then take that with you and start doing some problems. What do I mean start? Continue doing problems. Okay, so that was the grand finale. We went from reacting nitriles to preparing them, and they're very useful. The only sneaky thing is watch out for that one extra carbon that gets added when we add them onto something, okay? Signing out.